Alright, thank you for watching, and today as another analysis special, I want to discuss the concept of covering compactness, which is a concept that confused the hell out of me when I took analysis. But it's very hard to digest at the beginning, but I promise you, once you get used to it and you learn it 50,000 times, it'll make sense and it's awesome. Okay, so let me give you a little glimpse into its awesomeness. And it goes in two parts. The first part, I'll define what it is, and the second part, I give you a cool analysis application. So here's the setting. Suppose you have a subset U in Rn, or in any metric space, or even topological space. So you have U, and think of U as some domain or some rug, and you want to patch it up with little quilts. Okay, so you want to fill it up with little, not even circles, but just open sets, just like a quilt here, or patches, I'm sure you've seen those kind of comforters or something that look like those. Okay. Technical difficulties. Okay. All right. And if you take U and you cover it with those sets, it's what's called a covering. So here's a definition. Namely, a covering of U is a family. Think of a sequence except you could have like as many as the real numbers or any number if you want. So a family, let's call it UI where I is in some index set. Okay. So family UI where, so imagine you have this cover UI. If you take the union of all those patches, it actually covers your set. Is a family UI such that, again, if you take the union I over your index set of UI, it's actually bigger than your set. So it literally covers your set. And of course, in theory, you could use infinitely many of those coverings, or you can even use uncountably many of those coverings. If your set is compact, and this is what makes compactness so great, you never ever need infinitely many of those. Namely, no matter which covering I give you, you always just need finitely many of those. So definition, U is compact if for any covering ring UI, just finitely many of those suffice. So you can find finitely many. Let's call it UIK, I guess. So some subsequence, if you want, where K is from 1 to n. So you can select just a couple of those, finitely many, that still does the correct job. Such that if you take the union of those UIKs, K from 1 to n, it still covers your set U. Of course, in this picture it's a little bit silly because there's no way I can draw infinitely many of those. But if your set is compact, it just means you can select finitely many of those out of all those patches, you can select finitely many of those, such that it still covers your set. Again, let me emphasize. Suppose there's a salesperson that says, I pay you $1 for every patch. Then, if your set is compact, you never have to pay infinitely many dollars. You always pay some finite amount. Okay? And of course, it still might be confusing. Let me give you a couple of examples, because I think the best way of understanding compactness is to understand what not compact is. Sort of by the opposite. Okay, for example, let's choose an infinite set. Non-example 1. I'm claiming that 0, infinity is not compact. What does that mean? It means that we somehow have to cover that set such that you really need infinitely many of those to cover it. For example, choose this. This is your set 0 infinity. Consider the following cover. U1 is the interval 0 to 2. U2 is the interval from 1 to 3. U3 is the interval from 2 to 4. Etc., etc. We define this. U1 is 0 to 2. U2 is 1 to 3. U3 is 2 to 4. Etc., etc. Now, of course, there are a couple of ones I think that you can just get rid of. Like if you choose 0, 2, and 1, 3, and then another one, then you don't, like 3, 5, then you don't really need 2, 4. But the thing is, you really need infinitely many of those to cover it. Because if you say, hey, I only need U1 up to U of 9,000, then what about the point, 20,000? That one's not covered. And so, in fact, you see that for every point, you do need, some cover. So we really need infinitely many of those to cover 0, infinity. Really need infinitely many UI to cover 0, infinity. And in fact, for any infinite set, it's not compact, because let's say you find a finite covering. Let's say someone tells you, hey, you only need 9,000 of those sets to cover it. Well, because you're finite, just pick the largest element. Let's say the largest element is 20,000 of all those coverings. Well, what about the number 25,000? Then you have a problem. I showed you there is one covering which doesn't reduce to a finite subcovering. Here's another nice example. Example 2. R, if you take the whole real numbers, it's not compact. So, again, let me tell you an example of a cover where you really need infinitely many of those. Namely, if you want, suppose you have 0, let your first cover be -1, 1, your second cover be -2, 2, your third cover is -3, 3, etc., etc. In other words, UN is -n, n. And again, for this cover, you really need infinitely many of those to really cover the whole set. Because, again, suppose you just say you only need finitely many. Let's say you need everything up to U of 27. What about the number 28? It's not covered either. So again, really need infinitely many un to cover R. Therefore, I have shown an example of a covering of R that does not reduce to a finite subcover. So, and as I said, in general, using these ideas, any infinite set is not compact. What about finite sets? What about the interval 0, 1? So you have this. And in general, this also works for open intervals. I'm claiming, or at least intervals that are not closed, okay? I'm claiming that this interval is not compact. And for this, again, let me give you a covering where you really need infinitely many of those sets to cover it. Namely, let V2, let's start with 2, be 1/2, 1, V3 is 1/3, 1, no, etc., up to Vn is 1/n, 1. So something like that. That's V2, that's V3, ... Vn. And again, notice here, you really need infinitely many of those Vn's to cover it, because suppose you only had finitely many, and suppose the largest one would be V of 25. Then the question is, what about the number 1/26? It would not be in your cover. So by this quick argument, we find that we really need infinitely many Vn's to cover a 0, 1. Infinitely many Vn to cover 0, 1. In other words, there is a covering that I've shown here where you really need all of them. And compactness is the opposite. Compactness means no matter which covering I give you, you never need infinitely many of them. You always need just a finite number of them. So you would not spend an infinite amount of dollars to get all those patches. Okay, and now after this really quick introduction to compactness, let me actually show you why they're so useful. And I agree, it's a very abstract definition, but somehow you have to think of it as magic. Namely, once you know your set is compact, bam! Something happens, and you can use this bam to conclude your proof. And also the idea is, with finite sets, you can do stuff that you cannot do with infinite sets. And I'll give you an example of that. Therefore, with compact sets, you can do something extra that you cannot do with a non-compact sets. So, let me prove you a very classical theorem where you use compactness. So, part 2. So, theorem. Maybe write it in red. Suppose you have a function from a compact set to the real numbers. So if U is compact, and you have a continuous function, f from U to, let's say, the real numbers is continuous, you can generalize, it's not a problem. So it's continuous, then f is in fact uniformly continuous. And I forgot to say, U, let's say, is a subset of Rn. Doesn't matter. Namely, a continuous function from a compact set is automatically uniformly continuous. And let me quickly recap the concept of continuity and uniform continuity. So recall, maybe ironically, you may not never have heard it. So f is continuous if for any x, so for all x and all epsilon greater than 0, there is delta greater than 0 depending on x, and of course epsilon on x, such that if you have y minus x is less than delta, then f of x minus f of y is less than epsilon. So, for continuity, the delta could depend on x. Uniform continuity just means the delta does not depend on x. So f is uniformly continuous. So not University of California, which is great too. If for all epsilon greater than 0, there is delta greater than 0, not depending on x, such that if, again, for all y, if y minus x is less than delta, then f of x minus f of y is less than epsilon. Perhaps the most confusing concept in analysis, continuity versus uniform continuity, and the only difference really is where we put the, of course I forgot the most important part. There is delta such that for all x, if y minus x is less than delta, then f of x minus f of y is less than epsilon. So, as I said, the most confusing concept in analysis, and the only difference is, for continuity, we put the for all x outside. For uniform continuity, we put the for all x inside. And you might think that, oh, those are the same definitions, but not quite. Because this is better than continuity. And let me give you a little example, a little heuristic. Main important point is, for uniform continuity, the delta does not depend on x. So, for example, take this function f of x equals to 2x plus 3, okay, from R to R. R to R. Looks something like that. In this case, if you do the epsilon delta proof, delta would be epsilon over 2, and this does not depend on x. So the point is, this function here is uniformly continuous. And what this really means is that no matter where x is, the continuity is the same. So the rate of change is sort of the same. So if you choose an x here, well, the delta is still the same. If you choose an x here, the delta is still the same. So f sort of changes the same way for all x. On the other hand, take f of x equals to x squared. X squared from R to R. Again, our parabola. If you do the epsilon delta argument, then more or less, that's slightly confusing, you should find delta is epsilon over x plus y. And heuristically, it's not a proof, but heuristically delta depends on x. And in fact also on y, on x. And therefore, this function, heuristically, it's not uniformly continuous. And what that really means, it means that the change in f depends on where you locate it. So if your x is here, f changes just a little bit. So the continuity is a little bit. But if x is here, you notice the change is a lot. Okay, it changes much faster at this x than at this x. So it's not uniformly continuous. It's not continuous sort of at every step in the same way. Whereas in this example, it is continuous sort of at every step in the same way. And what I'm trying to show now is, if the domain is compact, every continuous function is uniformly continuous. And let's show that now. See, this is a very nice example of an analysis proof. So one of my favorite ones. So proof. Of course, what do we do? Let epsilon be greater than 0. So a weapon of math. And so the first step is, okay, let's use the definition of continuity, right? So since f is continuous, we know that for all x, there is delta, and again, delta depends on x. So if you think it's a function of x, such that if y minus x is less than delta, then f of x minus f of y is less than epsilon over 2. So technically epsilon, but we're allowed to choose any epsilon that we want. So in particular, you can find some delta such that if y is close enough to x, then f of x is close enough to f of y. And here's a picture if you like. So we have our set U, that's again compact, and we have our set X, and what it says is, if you're close enough to X, in particular with the radius of delta X, so if Y is in that ball, then we know that f of x minus f of y is close. So f of x minus f of y is less than epsilon over 2. And the point is, we get that for every x. If x is here, we may have a different radius, delta x, and if with x is here, we have a different radius, delta x. Of course, you may guess what I'm getting at, because for every x we have this delta x. Let's actually cover our set with those delta x's. And in fact, we want to do something slightly more than that. We want to get a little bit of wiggle room. So instead of choosing the balls of radius delta x, let's choose balls of radius delta over 2. And again, you'll see it's useful in a second. So delta over 2. So now cover. So consider the balls. Again, every ball is centered at x, but this time it has radius delta x over 2. And this is, let's call this thing ux, okay, just to make stuff easier. And notice every x every x is in fact in ux. So in other words, every point is in one of those balls. And u is in a ux. So that's a little remark. But that's super important because every point is u is in ux. In fact, you can cover the whole set with those balls. So consider cover. Namely, ux, where x is in u. So in other words, cover the set u with balls of radius delta x over 2. Again, something like that. You have x, and you have the little balls, da 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 da. And in fact, this is a cover of U. So, okay, so this is what I wrote. It's a cover. All right, and now we found a very strange cover, and now because we use compactness, bang, some magic happens. Compactness tells us that we only need finitely many of those. So we can cover U with finitely many of those balls. So since U is compact, there is a finite subcover. Subcover. Let's call it ux1 up to uxn. In other words, you can cover it with the union of those finitely many balls of b x1 xi delta xi over 2. So again, another picture. You have u, and then you just need finitely many of those points. Let's say x1, x2, xi, xn. And once you have those finitely many balls, you can actually cover your set. This is a bad picture, but it's supposed to cover your whole set. And let's see what to do with those, okay? And as I said, compactness allows you to do things with finite sets that you couldn't do before with infinite sets. And in particular, what's nice about finite sets, if you take, let's say, n numbers, where n is finite, you can actually find the smallest one of those numbers, namely the minimum, which again is not the case for infinite numbers. Step 2. And remember, our goal really is to find a delta that works for all x. And now we can do this. So let delta be the minimum of all our radii. So delta x1 over 2, delta x2 over 2, delta xn over 2. And the point is, if you take the minimum of all those finite numbers, something like that, this is, let's say, u delta, this is positive. Again, because we have finitely many numbers. This is super crucial, maybe the most important part of the proof. Because if you had infinitely many numbers, something like that, and you took the minimum or the infimum, it could be 0. And that wouldn't really work because you want delta to be positive. Not only do you have finitely many numbers, not only do you have a positive number, but moreover, this thing, because we have this cover of u, it doesn't depend on x. It's one universal number that works for all x. So, moreover, delta doesn't depend on x. On x. Again, and that's because if you're in one of those sets, because we have those balls cover every element of u, somehow this thing does not depend on x at all. It just depends on those n numbers, but since we take the minimum, it doesn't really depend on them either. Okay, let's show now that this delta does the trick. Let's show that this is the answer to all our problems. So maybe, that's step 2. So claim for all x and y, if x and y are close enough, then f of x minus f of y is less than epsilon. And once we have that, we're done, because then f would be uniformly continuous because we found a delta that's universal. That works for all x. Okay, and here comes a little bit of geometry, if you'd like. So there's a bit topological argument. So claim. So first of all, suppose x is in U. Then, of course, x must be in one of those covers. So then, x is in ui, which is again bxi delta xi over 2 for some I. I'm claiming the following, and again, you have, this is ui, and this is x, ui of center xi and radius delta xi over 2. I'm claiming if y, so this is x, if y is close enough to x, then y is also in the same ball but of larger radius. So maybe it's in there. So I'm claiming that if you take the ball of radius xi and of center xi and radius delta xi, then I'm claiming that y is in that ball. So bxi delta xi, which explains why we chose this delta over 2. Okay. If x minus y is less than delta, then y is in fact in this bigger ball, xi delta xi. Why? It's simply just a little analysis argument, because let's calculate the distance between y and xi by the triangle inequality. That's y minus x plus x minus xi, or I guess x minus xi. But now, we know that x minus y is less than delta, so this is less than delta. And now, x minus xi, remember it's in this radius, so plus delta xi over 2. But now, remember, we chose delta to be the minimum of those delta xi over 2s. So this is less than or equal to delta xi over 2 plus delta xi over 2, and that's delta of xi. So it works perfectly well because of our choices of this 1/2, etc., etc. And that's very good, because if y is in that ball, then we have the following. So, y in being in that ball, xi, delta xi, this implies, again, y minus xi is strictly less than delta xi. And remember, what is delta xi? It's precisely the delta of continuity of f at xi. So for sure what we have then is that f of y minus f of xi is less than epsilon over 2. Again, by definition of delta xi. And now we're almost done, again, by this triangle inequality, because what is f of x minus f of y? Again, by the triangle inequality, this is f of x minus f of xi plus f of xi minus f of y. This we've just shown. This is less than epsilon over 2. And then Then, because for this thing, remember that what is xi? It's precisely the point where x is in it, right? Remember we said, if you pick a random x, it is in the set ui, right? Which means that x minus xi is less than delta xi over 2, again, because xi is in ui. Oh, sorry, this is x is in ui. But then, what is delta over 2? In particular, we have x minus xi is less than delta xi. But then, by definition, again, because of the definition of delta xi, we in fact get that f of x minus f of xi is less than epsilon over 2. I think that's by definition of delta xi. And therefore, summa summarum, so in the end, we get that this is less than epsilon over 2, this is less than epsilon over 2, so let's just add them up, and then we get the following. Let's see. And therefore, f of x minus f of y, this is less than or equal to, if you want less than in this case, epsilon over 2 plus epsilon over 2. And then here comes a satisfying moment in every analysis proof. This is epsilon. So, in fact, we've shown that if x minus y is less than delta, where delta does not depend on x by compactness, f of x minus f of y is less than epsilon. And therefore, f is uniformly continuous. And now we are done and we can go home happy. But you see, the compactness here was very crucial because otherwise delta would have been 0. And as I said, with compactness, you can do stuff that you can do with finite sets, but cannot do with infinite sets. So remember always this property. It's super, super useful. Alright, and so we're done and we can go home happy. And if you like this analysis and like math in general, please make sure to subscribe to my channel. Thank you very much.